There are a number of debugging tools that will help you detect the most common unlucky C bugs. 1Valgrind is among the most popular of these, and this lecture segment will walk you through a simple use of it. We'll be using 1Valgrind to find errors in the example code malloc-mess.c here. The program has 4 major errors, and question 1 is, start by finding the 4 errors in malloc-mess.c, so we'll know what to expect 1Valgrind to find. After a pause, the answer is, let's see here, on line 9, we copy a string of 17 characters, if you count them out, remember the null at the end, into a block of 16 bytes. On line 13, we abandon an unfreed block pointed to by block 1, and on line 15, we use an uninitialized variable tests, and then on lines 15 and 16 here, we use a just freed block, block 1. Now, in typical C fashion, a run of malloc-mess, the executable, shows absolutely no errors. All 4 of those bugs are unlucky, assuming we expected test to be 0 in this case. So let's see what 1Valgrind has to say. And note the pronunciation, by the way, with a short I. It's not some contraction of value grinder. The name comes from Norse mythology. It's the term for the gateway to Valhalla. So this is typical tech intellectual whimsy. Now, running 1Valgrind can be quite simple. However, it does run only on Unix systems, so I'm going to bring up a Unix login over here. And we'll do a gcc of malloc-mess.c to the executable malloc-mess. And by the way, in this case, it actually has a test that is initialized to 1. But in any event, there's still no seg faults. So once again, a bunch of unlucky bugs. Then to run 1Valgrind, you just give 1Valgrind followed by the name of the executable you want to run. And you get a whole lot of stuff. What 1Valgrind does is temporarily adds to the executable code that checks for allocation errors, memory overruns, and uninitialized values. Then it runs the executable and reports any errors detected by its added code. There are many additional command line options you can give 1Valgrind to do deeper checks, but the default execution is sufficient for most cases. And as you can see from the run here, 1Valgrind's pretty chatty. It's not generally necessary to understand everything it outputs, and it often outputs multiple complaints stemming from the same error. We'll look at how to interpret the errors in malloc-mess.c in the diagram where I show them as a comment. But first, let's fix an immediate problem. If you look at the error messages here on the Unix listing, what you'll see is that the locations at our source, like main here, at which they occur, are given in terms of binary offsets into the executable. This is not very useful. We can get locations in terms of C source lines if we add debugging information to our executable, which we can do with the command gcc-g malloc-mess.c, thus. And if we then rerun 1Valgrind, what we'll see is that we now get line numbers, for instance, malloc-mess.c 13 here, at which the errors occur. The G option on GCC, the -G option, causes GCC to add to the executable information about the original source code. Such information is used by various debuggers, including 1Valgrind. So our 1Valgrind output now shows original source locations. For instance, in the first 2 cases where we have an invalid write and an invalid read on lines 9 and 10 of malloc-mess.c. Here and right here. These involve, again, as 1Valgrind output shows, the block allocated on line 8. And looking back up in the code, we can see that that's the 17th byte being written past the end in the stir copy and then read by the printf on line 10, so it got the bad read as well. So let's see, next up is our use of uninitialized variable here, test, on line 15, and that shows down here in the Valgrind output. Getting information on uninitialized data use is especially valuable, since this is the sort of thing that's often missed in a test. And it's almost as good as coding in Java. Using the freed data pointed to by block 1 on lines 16 and 17 here results in slightly different invalid read-write outputs or errors, complaining here about use of freed, as it says, data. And those will be repeated, by the way, for every offending read or write of that freed block all the way through the block. It does do a stir copy does do a full loop through it. And that's why I dropped out of the output here another 9 more complaints, each of them very repetitious. So that is a problem with Valgrind. You have to deal with a lot of extra data. Valgrind's not good at recognizing when the same basic bug is being uncovered repeatedly, and so you have to kind of read through the repeat errors yourself. And then finally, the unfreed block, that was the original target of block 1 up here on line 16, is reported at the end of the Valgrind output. Valgrind waits until the program's end to report leaked storage, since it can't be sure you won't free the storage until the program is done.